Okay, here's problem 2.7, and it's very similar to the last problem 2.6. There's just an extra phase factor in here. So some of the stuff some of the details I'll probably go through a little quickly, just because it was done in the previous problem. So we're going to start with this. It's in an infinite square well. So we want to know what the overall phase constant of the wave function, or we want to know how it comes into play. So overall, the phase constant of the wave function doesn't matter whenever you get a measurable quantity, but the relative phase can matter. So this is a relative phase difference. This is a difference between state 2 and state 1, which are both stationary states. So we want to find the time-dependent, the absolute value of the time-dependent squared, and the expectation value of x. And then we're going to be looking at like a couple obvious phases. So this is in a square well. So we have this result that we can build off of. And also I am going to use the normalization that I got in problem 2.6 part A, that A is equal to 1 over square root of 2. Okay, so this is also very much like problem 2.6 from separation of variables. I know that I just have a phase exponential time factor in there. I don't need to compute just like before, I don't need to compute the series of constants because I just have one constant for just two states. Okay, so here my square root of 2's cancel out, so I get 1 over the square root of A, and then I'm going to have sine E1. Oh, and I'm going to just use E1 and E2, and we're going to be using the fact that E2 is 4 times that of E1. Just like we did before. That's how we got that 3 omega. And I could say that E1 over h bar, we'll call that omega 1. E2 over h bar, we'll call that omega 2. So then I can go ahead and write this as I omega 1t plus sine 2 pi a x, and then we have e to the I phi, and we have e to the negative I omega 2t. So we could also pull that out a little bit like we did last time. Let's pull out this e to the negative I omega 1t. I could just call it omega t, I suppose, because now that we have pulled it out, And then that's going to be negative 3I omega 1t. Just like we had before, except we have that extra phase constant. And then if you want to get like really into it, you could put those all in the same exponential if you like. Okay, so exactly just like the previous one, except for this e to the I phi phase constant. Alright, now let's get into this part. None of this is really groundbreaking because it's just really basic algebra like we did before. So we get 1 over a, and then I have e to the I. I'm just going to use omega because they're now the same. That cancels out. Now, I said before I don't like have any math pride or math balls, so I'm going to just like work it out. I get sine, this first sine term squared. It's the same sine term because I didn't have, there's no imaginary term there at all. Now my second one, I'm going to have this one times its complex conjugate. So, and I'm just going to write it all out. Then I get e to the I phi times e to the negative I phi, e to the negative, even though this all is going to cancel out. So those all go to 1. Okay, then we have the cross term. So then I'm going to have this first term times the complex conjugate. I'm just going to go down to new line. So I get this guy times the complex conjugate of that guy. Negative. And this will be positive. And then the last one, then we're going to have this one, this first term, and it'll be times that term in the complex conjugate, which is the same. So we're just going to write that one first, and then we write this. So it is exactly what we had last time, just this extra phase factor. Okay. Now I'm going to clean that up just a little bit. Make it a little bit more clear. So I get 1 over a. We get our 2 sine squared terms, just like we had before. Oops, sine squared. That should be squared. Those all go to 0. And then we're going to pull these out. Our 2 sine terms. And those are multiplied by e to the negative and positive plus e to the positive and then negative. There we go. Okay. Now we can use the same trick we had before. Like the Euler relationship. So I might want to gonna do one more simplification to make this a little bit more palatable. But you know where it's headed. We're going to get two cosines instead of those exponentials. So we're going to have e to the negative. Actually, we'll just call that one positive. So this will be e to the I 3 omega t minus phi. And this one is going to be e to the negative I 3 omega t minus phi. So then we know that if we have e to the phi, that equals cosine phi minus I sine phi. So if I have this relationship, then my cosines are going to add together and my sines are going to cancel out. So just rewriting this first part. And that just is going to simplify to 2 cosine. So I suppose I should put the 2 out in front. So then I get 2 cosine of 3 omega t minus phi. And end bracket. So pretty much exactly what we got for problem 2.6. We literally just have this extra phase factor out in front of there. That is it. That is all we have that is different. Other than that, everything is the same. Okay. And that, the last thing we wanted was, so that covers us for our time dependent squared, and then we want expectation value. Got quite a bit of room, so let's go ahead and give it a shot, see if it's gonna work. I'm going to do the same thing like I did before, which is just breaking it into 3 pieces. So our expectation value comes from integrating this guy times x. So our expectation value is going to equal a 1 over a. And let's go ahead and break it into 3 pieces. So we're going to have 1, 2, 3. So 1 is going to be 1 over a. We integrate from 0 to a, that's the width of our well, dx sine squared pi over ax. We can do a u substitution there. U equals pi over ax. Oh, whoops. X. We need an x in there. So that means x is going to equal u a over pi du dx it's pi over a dx. So dx is du a over pi. So I'm going to get a factor of a squared over pi squared out in front there. My limits, u1 is going to equal 0 and u2 is going to equal pi. I'm going through this quickly because we already did it before. Okay, so I get a squared over pi squared times 1 over a, so that's just a over pi squared. 0 to pi du u sine squared u. Okay, we integrate by parts. U dv equals uv evaluated at the limits minus v du. Probably, let's go ahead and change those guys to y's to make it more clear. Okay. Now, my u is going to equal y so that du can equal 1. So the entire point of integrating by parts is so that I can take the derivative of something and hopefully get rid of it. Not always possible in one step. So then dv is sine squared y, and v is this integral that we have done many times at this point. So suffice it to say, the integral of v is y over 2 minus 1/4 sine 2y. Oops, that's a 1. So my expectation value of 1, the first one, oops, is going to be u times v, so that's going to be y squared over 2, and 0 is not going to equal anything, so that's going to be pi squared over 2, and then sine evaluated at 0 is 0, and sine evaluated at 2 pi is 0. So I just get pi squared over 2, and then that's going to be minus the integral from 0 to pi dy of v du. So then that'll be y over 2 minus 1/4 sine 2y. Okay, so my two integrals there. The first one is going to be y squared over 1/4, so evaluated pi squared over 4. And then my second integral is going to have a 1/8 out in front, and then we are going to have a cosine of 2 pi minus cosine of 0. Cosine looks like this. That's 0, pi, 2 pi. So that's 1 minus 1, that equals 0. So that means I get the same exact expectation value for the first part that I did before. My pi squares cancel. I get a times 1/2 minus 1/4. That is a fourth. My second expectation value is the same, and that's because everything works out the same. It's just when I do the u substitution for part 2, my u equals 2 pi over a, so whenever I have a pi here, I get a 2 pi for the second part. Okay, now then you can also, I did just for fun one time look that up on like just plugging it into like Wolfram Alpha. Of course I got the same thing. It's a good way to check your answers though. Alright, now x3, here's the hard part. This one's going to be 1 over a, and then I have from 0 to a dx sine. Now, in the last problem, I did this by using a trig ID, so I was kind of thinking that's a 2. Maybe I'll just do something different just for fun. Because it's the same exact thing. As you can see, the cosine doesn't depend on x. I always forget to put that x there. My cosine isn't depending on x, so I can pull the cosine that I have out there in front. Now, last time what I did was I used this identity. Sine u minus sine v equals 1/2 of cosine u minus v minus cosine u plus v. And that breaks this down into a couple of pretty easy integrals. Now I'm going to just use an integral table result that I have. Let's see if I can find it. I believe it's this one. Nope, not that one. There we are. Okay, so let's go ahead and use this result. Let's try to make that a bit bigger. There we go. Now certainly the other method works just fine. You could do the same thing again, but this is another way to approach it. This is just from a standard integral table. And let's go ahead and plug this in just to keep things straight. My a equals pi over a, and my b equals 2 pi over a. No, let's do it the other way, so we don't get any negatives, because I'm going to have a minus b, so I want that to be a, and I want that to be b. Alright. So we have 2 cosine 3 omega t minus v And then we have from, let's just go right to here. We get a 1/2, just like we did before. So we get that 2 cancels out. Now we have x sine of 2 pi over a minus pi over a. So that's just pi over a x over 2 pi over a minus pi over a. So that's all over pi over a minus x times sine of 3 pi over a x over 3 pi over a. Those are going to just go away with our limits, yep. And then we're going to be left with cosines. So that's going to be cosine of just pi over a x over pi over a squared minus cosine 3 pi over a x over 3 pi over a squared. And that's the exact same, like, that's just several steps taken out when we did it before, where we changed it to cosine and then integrated by parts. Okay, now we can simplify that up. Oh, and then my limits 0 to a. So what that means for my limits, I just get cosine 3 omega t minus phi. And then I can go ahead and cancel out this. Well, we'll just leave it for now. Let's say that's a. Okay. Now, here, I have a squared over pi squared times, and then I get cosine of pi minus cosine of 0 minus a squared over 9 pi squared, looking familiar, cosine 3 pi minus cosine 0. So going back to our cosine, so that's pi and that's 0. So we get -1 minus 1, -1 minus 1. So that's -2. I am going to go ahead and factor out the a, so the a cancels, the one on the bottom. I get a pi squared out here, and I get -2, and then I have -2, so I can go ahead and get the 2 out. And why don't we just, I will leave it in there. So then I have 1, -1, 9/9 plus 1/9. So my third expectation value is going to be equal to negative 8 times 2 is 16 a cosine 3 omega t minus phi over pi squared. Just like we had before. Oh, and a 9. Forgot about the 9. There we go. Okay, now if we put those all together, let's go ahead and do that. So problem 2.7, my expectation value is going to be from the first one, A plus, and then we had 16 A cosine 3 omega t, minus phi, all over 9 pi squared. Or we can make that a half plus 16a, so just below a half, and then we have a pi squared cosine 3 omega t minus phi. Very close to what we had before. Literally the only difference is that guy, that phase factor. So if phi equals pi halves, then that just means that this goes to a sine wave. It's just phase shifted 90 degrees. So it's a sine wave. It's exactly a sine wave. So then we have sine omega 3 omega t. If this is shifted by pi, then we just get a negative. We're 180 degrees out of phase. We're pi out of phase. So we just get negative. Oops. And that's it. So if we shift it backwards pi halves, then this goes to here. Shift it forward pi halves, then this goes here. Get a sine wave, cosine always leads cosine. If I shift it by a total of pi, then this goes to here, so I get a negative of my cosine. And that is it. That was a lot shorter than the last one.